Okay, and welcome to our first lecture for grade 12 chemistry on quantum numbers. As you can see from the front here, the first slide, our learning goal for this lecture is to be able to describe the size, shape, and orientation of an orbital using what we call quantum numbers. So let's get started. So first off, what is an orbital? Here's your actual definition. An orbital is a region of space around the nucleus where an electron is likely to be found. So in the past, you guys have seen orbitals that look like this. Okay, we've drawn sort of rings around the nucleus. And you have heard in the past that that's not entirely accurate. So what we're learning today is how this changes. But we're still looking at these sort of different energy levels or these different orbitals as places where electrons go. So let's go back to this slide, and we're just going to go through a couple of points here. Werner Heisenberg, who was a student of Bohr, realized that to measure a particle we have to touch it. To measure subatomic particles, we did that by sending photons to collide with it. Now here's what happened. They were able to find out lots about protons and neutrons, but electrons were actually too small and moved too fast for our technology to observe exactly where an electron is located. So because of that, we have these two, this principle of Heisenberg's uncertainty principle. And he basically said that it is impossible to simultaneously know the exact position and speed of a particle. So that basically means that if we know the position of a particle, we cannot determine how fast it's moving, or if we know how fast a particle is moving, we cannot determine its actual position. And such we get this three-dimensional orbital diagram, which is also called an electron probability density. So this is sort of a 3D representation of the chance of finding an electron in a given space. So that is what an orbital is. So this is what we're going to be learning about, and today we're actually going to see what the shapes and what these orbitals actually look like, and we're going to use quantum numbers to describe them. So back to this side, back to this picture, we're looking at, here's a diagram of different energy levels, and now we're going to actually start calling them orbitals. And you can see right now that each sort of energy level coincides with a row on the periodic table, which is also called a period. So if you have something in the fourth energy level, you'll see it in the fourth period on the periodic table. It can be any one of these elements. Alright, so now quantum numbers. We use these quantum numbers to describe the orbital in which electrons can be found. Now the neat thing about this is that every electron ends up having its own individual set of quantum numbers. So we're going to start, there are 4 different quantum numbers that we're going to learn about today, and on this slide we're going to talk about 2. So the first is the principal quantum number, which is denoted with an N. Okay, and it describes the size and energy of an orbital. So we start with n equals 1, so that's the first energy level, up to basically infinity. We only really go as high as 7 on the periodic table, but theoretically we can go up to infinity. So the higher the number, the bigger the size, and the more energy those electrons in that orbital have. The second quantum number is the angular momentum quantum number, and we denote that with an L. This describes the shape of the orbital. It's also called the subshell number. The allowed values are L equals 0 to whatever your value for n is, minus 1. And then what happens is each one of these quantum numbers, each subshell number corresponds to a letter. So if we have the subshell number 0, we call that S. If we have a subshell number 1, we call that P. Subshell 2 is D. Subshell 3 is F. Now I know this is all very new for you, so what I'm going to do on the next slide is actually show you a picture of what this looks like. So here are some different subshells. Okay, we've got a quantum number of L equals 0. What that does is that gives you what's called an s orbital, and an s orbital is usually in the shape of a sphere. If L equals 1, we have what's called a p orbital, and a p orbital is usually in the shape of sort of like an infinity sign or a dumbbell shape. Okay. If L equals 2, we've got what's called a d orbital. There are actually many variations of a d orbital. So here's actually 2, where you've got sort of 2 dumbbells that are crisscrossed. And lastly, the one that we're going to look at is L equals 3. That is an f orbital. And you can see that basically as your L values increase, your orbital shapes become a lot more complicated. I will never ask you to draw something of a d orbital or an f orbital. You will be expected to draw s and p orbitals on a regular basis. So we're going to look at that, and we're going to look at what I actually expect you to be able to do with this after. Alright, so the last 2 quantum numbers are number 3, the magnetic quantum number, which is denoted a lowercase m with a subscript L, and it describes the orientation of the orbital. The allowed values are from negative L to positive L. So we'll look at what that means after. And it basically takes into account that there are 3 dimensions, okay? So you can have an orbital lying on the x-axis, the y-axis, and the z-axis. The last one's probably the easiest to grasp, is the spin quantum number. It's denoted m with a subscript s. Describes the spin of the electron. And the allowed values are plus 1/2 or negative 1/2. Or in some textbooks you'll actually see it say +1 or -1. All it means is that electrons can either spin in one direction, call it clockwise, or the opposite direction, counterclockwise. So we use positive to denote one direction and the negative to denote the opposite direction. Alright, so here are some examples of the m orbital, okay, looking at the p orbitals. So here are p orbitals. When my L value was 1, that gives me an ML value of -1, 0, and +1. Because remember that L can go, your ML values can go from -L. Oh, my thing isn't working. We can go from -L up to +L. So here's your negative L value, -1, 0, and +1. Those end up being the 3 separate orientations on your x-axis in pink, your y-axis in yellow, and your z-axis coming straight out at you. So here are 3 different orbitals where we could basically find an electron. Here's sort of another way of looking at it. These are basically a similar diagram. This is sort of more in tune with what it actually looks like in reality. Alright, so when L equals 2, we've got d orbitals, and like I said, as you increase your number for your L, and you go from an s to an p to a d to an f orbital, the orbitals actually start to look more complicated. So you can see we actually have those sort of 4 dumbbell shape orbitals, and they're each in a different orientation. So here they're flat, here they're kind of straight up, here they're flat but they're twisted a bit, and here they're straight up but twisted a little bit. And then you've got this weird fancy one, which is just kind of unusual, but it does exist. So again, I will never ask you to draw any of these, but just please know that they exist, and that there are 5 d orbitals. So the d orbitals, because your L value is 2, we go from an m value of -2 all the way up to +2. So each one of these corresponds to a different orientation of your d orbital. Okay, so here is basically your new picture of what an atom looks like. So this is actually a krypton atom, and it's all I'm trying to do by showing you this diagram is to basically show you how complicated it is when we're actually drawing orbitals. I will never ask you to draw anything like this. I cannot draw anything like this, and I don't expect you to. But what you can do is you can see how the orbitals overlap. You can see how they get bigger. So you start off sort of in the middle here with 2 smaller s orbitals. Okay, and here's a really big s orbital. Okay, and we've also, you can see some p orbitals that are gradually getting bigger. So here's a small yellow p orbital, right? And you've got one there. You've got a small pink p orbital there. Okay, and then you can also see them getting bigger. Here's a large, big p orbital there. Okay, you can also see, I can see one of the d orbitals. Okay, and it's these 4 blue things that I'm sort of outlining with my cursor here. So that's one of the d orbitals. Okay, like I said, I'm never going to ask you to draw this. I'm just trying to show you this so you get a representation of what an atom actually looks like now. So there are electrons in each one of these little bubbles, and they're not just in pretty rings around the nucleus anymore. It gets a little bit more complicated than that. So the last thing I'm just going to show you is the periodic table here, and how they actually define the periodic table. So the first two columns on the left here, this is when L equals 0. When L equals 0, we've already defined that as s orbitals. So all these blue here, all the atoms that fall in here, so hydrogen, sodium, calcium, strontium, all your elements in here end up having your outer electrons with an L value of equal to 0, and they're in s orbitals. The positive and negative spins end up being what gives you the two columns. If we go over, we're going to skip the d orbital for now. If we go over to the p orbital, I told you before that if you have a p orbital, that means your L value is 1. And if your L value is 1, that means your ML values are from -1 up to +1. But what ends up happening is this actually gives us 6 electrons because we have 3 of them, 3 different electrons in 3 different orbitals that spin in one direction. And in those same 3 orbitals, you can have another electron that spins in the opposite direction. So that's why we've got the half spin here and the negative half spin there. Same thing with the d, except now because L equals 2, we end up having, we go from -2 to +2, so that gives us 5 separate orbitals. And then within each of those 5 separate orbitals, you can have 2 electrons. So that gives us a total of 10 electrons in each of those 5 d orbitals. Lastly is the F, which I'm going to show it to you, but I, again, don't expect you to be able to draw that or play with that, and we're not even really going to focus on it too much in this course. But again, you have something with a half spin and a negative half spin. So you've got your 7 orbitals here that each have an electron going, say, clockwise, and then in those same 7 orbitals, you've got electrons in them going in the opposite direction. So what we're going to do in class is we're going to look at how this actually works, how to define quantum numbers, and if we go back to our learning goal, back to the beginning, you should now be able to describe the size, shape, and orientation of an orbital using quantum numbers. So if I tell you that something has an s orbital, you should be able to know that that's a sphere. If I tell you that something has a p orbital, you should know that that's a dumbbell shape. So we're going to go through a bunch of examples in class. Thanks for listening.